Yes, I got it right. Thanks. All right, folks, I just checked my notes. Let me get this right this time. All right, so I'm going to do this. I'm going to tell you about the test, answer a couple of questions. Correct, actually. And then I do need to lecture because we're going to blow Wednesday on a review. That's normally what I do on the extra Fridays, but I really thought making, instead of doing a review right now for the test, instead of doing Wednesday was a major positive thing. And don't do things at the last minute. It's a good life habit, just in general. Sorry I got bitchy last time, but folks, you really are the best class I ever taught. I'm not doing that to stroke your ego. I don't need to. I'm tenure. I could just not be wearing pants right now. They couldn't do anything. Actually, they could totally get me arrested. But anyway, you guys are a good class. I want to make certain mistakes that way. I want to see you be the highest group of people I've ever had. Because right now your scores are 10 points higher than anyone else. I'm giving you all C. Right now, you're all going to be A's. So if you didn't do well on the homework, that's a sign. All right. Step it up, because I don't see a curve. You guys are just doing too good. So anyway, okay, what did I do? What did I do? Okay, change of work one needs to be integrated. And I know you use here to really gotten on me on this, so I'm trying to be much more careful. And into the limits of integration, which I did get right. Okay, and then the change of work two. Again, it needs to be integrated so that the little delta becomes a big delta. P2, B2, and again, that because of limits of integration. And so I did actually get it right the first time. That what I meant to do was to say that the change in U2 versus U1, what I screwed up is the net change in work. And so, yeah, that's what I screwed up. It's the net change. So I was always half right every time I screw this up. And that is just, again, what I said one time, which was correct, is just you add these things up and let them be negative or positive as they so choose. So I actually did get that right, and now I see U2 plus P2, V2 is equal to U1. There's our missing minus sign from the last time I did this. So H2 is equal to H1. Sorry for my crappy drawing, my bad handwriting, but I just got my cake wrapped there really badly. I hate it when I do that. And that drives you guys nuts when I screw up. So anyway, all right, so there it is. There it is. That's what I screwed up. Sorry about that. Thanks for your patience. And I'm going to try to write a nice handout for this because I always do that. I just really didn't have the time. Because they make me do so many other things, unfortunately. I have to run the department at some point, which would be crazy because I'm going to get overcome the monkey butlers. So, okay, last bit, then I'll answer just a handful of questions because today is technically a quiz day. Okay, on the test. Okay, on general, I am making you do a gas expands, a gas contracts, 5 liters, 4 liters, this, that, calculator, calculator, calculator. I have 2 spare calculators, and last semester, always 2 people showed up without a calculator, so that worked out. Bring your calculator. How much of it is calculator work, which I know you're very good at? About a third. So I'm not going to go beyond that. So bring your calculator, but it's not going to save you. Okay, because you're going to start out with true and false. And you're going to answer 4 out of 5 questions. As I mentioned to you before, you don't have to write this down, right? You're going to take the thing. You're going to see it. Just absorb. True and false. 2 statements. One's true, one's false. Let me give you an example. The units of volume are a meter cubed. The units of pressure are joules over meters cubed. The units of pressure, the SI units of pressure are atmospheres. Sorry, I told you 2 true statements at once because that's how my mind works. What are you going to do? You're going to say, the first statement was wrong. The units of volume are liters. Is that correct? Oh, Jesus Christ, whatever it was on the test. The units of volume are meters cubed. Right, the SI unit of length is a meter, so volume is actually meters cubed. Liters is a cheat. Liters is 1,000 up to 1,000 off. That's why I put liters and KPA together, because one's 1,000 times too big, the other is 1,000 times too little. That's why I can multiply them and cancel. All right, the second statement, which I already forgot what I said. Oh, I said the false statement is the SI units of pressure are atmospheres, they're actually pascals. All right, so what I want you to do is you have to identify what's wrong and say why it's wrong. Every time someone says, oh, well, this statement is correct. Well, I don't need you to tell me that. I already know that. No points. All right, now actually I'll give you half points. That'd be about 2 points. So you get the right thing wrong, and you don't say why it's wrong correctly, I'll give you half. If you do the opposite, I still give you half. If you identify the right thing wrong and why it's wrong, you get full credit. So again, just pretty clear. Somebody always screws this up. Again, just tell me what's wrong and why it's wrong. Okay, units. Okay, here's a good question. Pi is equal to kitties over chickens plus 1. Okay, what are the units of kitties? What are they? What if you said needles? Kitties has units of chickens. Why? Because it has to cancel, because I have numbers and numbers. Right, exactly. So there you go. I'm going to throw this at you. I'm going to do this, something just like this. It's going to be the majority of the questions are going to be lagged out. But that test whether you really got it or not. All right, so expect that for units. Now all these are about 1/5 of the test with some problem set questions. Problem set questions comes next. I think these are the titles of the 5 sections. Problem set questions. A gas expands this much. How much work and heat are generated? Simple one. All right, then I got life, the universe, and everything. So life, the universe, and everything, and that's 2 out of 3. What's that going to be? Work. Yes, it's going to be a gas expands. Give me the change in U, Q, H, T, V, T. Everything. It will be 80 of 80. Or simple derivation. Got 1 or 2 simple derivations from here and here, and then I got derivations itself. Derivations, and that's 2 out of 2. Sorry, I don't really give you an option on this one. And this is, I've already written one of them. It's going to be something like, what's the compression factor? What's the residual volume? I'm already doing that. You're going to have all the formulas on the cheat sheet, which I'll send to you on Wednesday. And what I'm leaning for, the second one, which I have not written yet, is going to be something like, okay, what's the change in H with respect to P at constant T? something like that. And then I'll tell you how to do the expansion. I'll tell you how to do the first step. I'm not saying that's going to be it, I'm just this is how I'm thinking right now. I'm sure this is how it's going to go. So anyway, that's the test, and I do need to get into material unless you have some questions. There's questions.
About the test, so for example, if you answer like 5 out of 5 of the true, so if you answer like 5 of the true false questions and you get one of them wrong, will you give us full credit?
No.
No.
What I'm going to do, you see, now I'm sorry, I should have said something already, it's my fault. What I do is I'm going to score the first 4.
Okay.
And the 5th one gets marked out, even if you've missed number 4 and got number 5 right, I don't care.
Okay.
All right, now the reason I'm doing that, I know it sounds like, oh, well, I guess this guy is a dick. Well, the reason is that one of you took the time to answer more questions. If I do that, you got an extra question that other people didn't. So someone who follows the rules and just answers 4 out of 5, and you missed one, and you missed one. Well, someone else took the time to answer a 5th, and then I say, oh, well, okay, I'll give them a break. That's like an extra freebie that the other person who did what I asked did not get. That doesn't make sense to me. So don't do that. That's, it's a good thing you asked that. The number one mistake people make is answering all the questions. Now, the sections are very cleanly divided. You're not going to get confused, and even if you do, so what? It actually doesn't really matter that much. But just don't get pissed. It happens every time that someone answers 5 out of 5, and they miss number 4. And so they only get 3, right? That's going to happen. Now, I need you to, I think that you would rather I did it this way, right? I'm pretty sure about that. One second. I think you would rather that, but that's how I'm going to do it, all right? So to make it fair, that's the only way to make it fair. And now what you do is when you see a section and you see a question that you're panicking on, like, oh shit, I forgot what heat is. Mark it out. It's gone. You don't have to answer it, right? So don't panic. And that's, I think, a very common thing. And then you miss the other one. But anyway, all right. You answered 5 out of 5 accidentally, which is very easy to do. You're kind of panicking, all right? So you answered 5 out of 5 and you realize it. Look at the one you're not sure about, cross it out. No, just seriously, I mean, I look for this. Don't grade, X, whatever. I get it. I won't grade it. So mark out the one you're not confident on. Right? That's a very good thing, in case you accidentally overdo it. Another question.
You answered it.
Oh, okay. One last question. You ready? I know I'm really bad at this. Oh, God. Here, I gotta try again. Now, if I don't, OCD. Oh, man. I was actually a professional baseballer. I'm actually a congenital liar. Anyway.
The derivation we did today, I think you said it, but just to clarify, it's definitely not something we need to be able to do for this test.
Oh, let's see, the ones I just did, too painful, too many steps. I'm going to try to keep it down to 3. If I'm really being a bastard, I'll have 4 steps at most, with the 4th step being the answer. I'll give you another good example, CP minus CV. Remember we did that, Monday? That was, we had to do a derivation, we had to do another derivation, we had to put the 2 together. It's too much. It's just asking too much. I don't believe in asking questions that I don't think you had any chance of answering, because what's the point? And then all of you, except maybe one of you gets it. Well, that's just frustrating. And I just don't see the point. And I know you're nervous. And I act appropriately. I want you all to get high scores. I want you to come out of here saying, yeah, I definitely answered more than I did. Because you know that we have people that you take the class, you answer 20% correctly, which is utterly frustrating, and you get a C. That sucks. All right, I'm not going to do that. So maybe, look, and I did warn you, some of you are not going to do well. A lot of you are not going to do well on the first test. You're going to figure it out. The first test isn't that many points. It's not going to really hurt you much at all. So you're going to take the first test. Most of you are going to not get the grade you want, and you're going to fix it. One of my top scores got a 60. That's a D, by the way. She got a 60 on the first test, and then it was 100, 100, 100. Second, third, final, 100, 100, 100, A. No problem. So that's a lot of you, by the way. So then don't freak out about it, right? And if you're really not doing well, you talk to me about it, okay? We'll fix it. Okay, look, folks, I do need to stop questions because I really do need to give a full lecture, and I will end on time. And again, office hours, how about we'll do 11 to 1, Tuesday, Wednesday, because I know your test is coming up. Email, whatnot, I am a little slow. I'll have the videos posted as fast as I can, but it could be as late as as late as Monday. It depends on the weather, in all honesty. Okay, so, back to, after, oh my God, what am I doing? See, I'm already screwing up. Of course, I'll be available after class. I don't have anything to do after class, so I can answer your questions then if you have questions. Okay, the question is this exact? Sorry, my handwriting's a little bad today, and of course, you know it's entropy. Entropy is a state variable, and entropy has to be exact. All state variables are exact. It has to be path independent, and that means my Euler criteria has to work. And I'll write that down again. Sorry, I'm singing a little song or something. I'm going to write down things I've already written. So again, the Euler criteria is this: permute your double derivatives, and this is going to come up. Y and X is going to come up when we do things called Maxwell relationships. So you'll see it one more time. That's about it. And all right, let me write down the change in heat from last time, and I won't do the derivation. Now we have the change in U with respect to temperature, constant volume, and then we had this. So this is the change in U, and then of course the change in work minus the change in work was PdV. Right. Okay. This is really CV dt plus PdV. So CV dt plus PdV is heat. Okay. I'm just choosing to leave CV in this form because it's just going to make life easier. And then I'm going to divide by temperature. And I'll do it this way over here. I know that doesn't quite look pretty, but it is what it is. Okay. Now what I want to do is, let's do this side, I don't know, this side, whatever. All right, let's do the change with respect to volume. Am I doing this right? The change of U with respect to T, constant V, constant T. And, oh, sorry. Folks, I'm really sorry about this. Sorry about this. I never try to overwrite my own derivations. Sorry, got to have that one with T there. That makes it different. Okay, now, at constant T, the last step is constant T. Now, when you're doing, because when I do an office hour, I'm not trying to make fun of you, I just want you to get this. Change in nRT, right? Remember when we said change in H is change in U plus change in PV. And then I said the change in PV is the change in nRT. What did I do to the nR? Took it out. Now, what if you said, oh, you should make it 0? No, you can't do that. You just take it out. Right. I wasn't making fun of you. I just want to point out, because that actually is a very natural thing. I can see a lot of people would want to do that. And so I just take it out, and actually I'm left with the same problem I had before. And if you don't recall, that's okay. I can permute this T, U, V, constant V, and that is, like last time, perfect gases. You did it just a second ago, yes, 0. There you go, just to remind you where that comes from. So you don't get lost in your own notes. Okay. Yeah, my handwriting is really fast. Sorry about that. Okay, that's one side. The other side, so from the change with respect to T, P over T. Sorry, let me write it out fully. Constant V. I already know that. So I have this side, that means I have this side. So this is the change with respect to T. P over T. Constant V. Again, the constant here doesn't actually change things. This is the change in N R over V. And, sorry. Come on. 0. Of course. Here we go. 0 equals 0. Therefore, right, this is a Huffy the Puffish question. It's like changing a goat with respect to a chicken. Sorry. sorry, let me, God, my handwriting's so bad, I don't know what it is. Exact. Okay, so there you go. 0 equals 0 counts in this case. I know, like, when you're solving a system of equations, sometimes you get everything is 0, and that is a legitimate answer, just not the right one. And then you say, well, okay, I screwed up somewhere. This case, no, it's fine. 0, 0, fine. So changing heat, right, there's only heat changes. Changing heat over T is actually exact. And if we look at the units, okay, heat is always a joule, not a joule per mole. Joule per Kelvin, joule per Kelvin. Partial or no partial, remember it has units. I'm sure I'm going to have that on the test. And that is the same as entropy. Okay, question?
This part in the middle, that's your whole right side of the equation?
Right here?
Yeah.
This is one side, just one side, this is the other side.
No, I mean like that whole derivation right there, that represents that right side of the above equation.
Oh, I'm sorry. This is just to remind you what I'm sticking into here.
Oh, okay.
Right, sorry, I should have put a blue line.
Okay,
Right,
gotcha.
so this is what I start with. I force it into this form. Remember that F was Q. If the Y would be, for those of you watching the video, which I think is going to be all of you, there you go. I should have written that down. Things get too obvious to me sometimes, and I don't say it as I should. So anyway, we're okay. Any other? I know you have a Hershey's Kiss. Anyway, any other questions? We're doing okay. All right, so now I have to get kind of ultra descriptive. I want you doing this. You're not going to see this again. This is a little thing in the rear. Again, another example of something I really, I mean, it's not that bad, really, but not in the test. I really don't. I see most of you starting out in the wrong direction and getting stuck. And I just don't, I think that's a waste of both our times. I think your test part is great, too. It better be really easy to do for me, in all honesty. So you see I have a strong motivator. This brings us to the second law. Second law. This is why this class exists. Understand the second law. First law, energy is neither created nor destroyed. It's easy. That's P equals nRT. That's not hard to imagine. I mean, I get that, you know. The universe is going to end as a gaseous, cold ball of hydrogen, and that sucks. Well, we're all gone at some point. But it still has energy. It's going to have the same energy it was created with. I don't know what that is, no one knows. Second law is a Bismarcker. And that's a southern expression for Bismarcker. And the third law, actually, when we get to it, the third law states that, yeah, the second law is really right. The third law only affirms the second law. That's the third law's job. Just to say the second law is actually, yeah, for real, dude, the second law is correct. The second law is very hard to understand. And there's multiple ways to express it that seem to have nothing to do with each other. So I'm going to start with the harder one because I like that. It tells you what you cannot do. What you can't do. And that is go on the road with Justin Bieber. Sorry. What it says is can't turn all changes of heat into a change of work. So you can't turn all heat to work. Now, let's see. Sorry, I haven't written my notes that well. Now that may already seem counterintuitive because at constant temperature, and this is one of the things, actually I'd rather you didn't write it down. Just to remind you, changing to a constant heat is 0 units equals the change in work plus the change in heat. And therefore, at constant temperature, the change in heat is equal and opposite to the change in work. Now, again, minus signs are a human convention. Nature doesn't know up from down, really. Gravity is a weak force in chemistry. We don't ever think about gravity. So nature doesn't see up from down. So this minus sign doesn't mean anything. But what I'm seeing here is heat and work being equal. Right? They're equal to each other. And that is completely counter, or apparently completely counter to this statement right there. Isn't it? Not see. Now, I actually wrote this. I did not say work into heat. I said heat into work. That means direction matters. So now, when I have the magic piston that I'm always compressing or expanding, I compressed, it got hot, and the heat came out. That was work into heat. And I did turn all that work into heat. And all the heat came out, whatever. All right, now this is heat into work. That's a different direction, right? So that means I can't heat a balloon, have it expand, and maintain a constant temperature. That would be crazy. That makes heat capacity and constant pressure infinity. Well, last time I checked, that's not the case, right? And that's the second law. It's just one of the consequences of this statement of the second law. And you know the other statement, that spontaneous reactions have a positive change in entropy. Anyway, that's the other statement. We'll get into it. So, okay, other examples. Let me give you a couple of examples so that however you kind of think about things, one of them will speak to you. Okay, I hit a ball on the floor pretty hard. Floor gets a little warm. Well, not really. Okay, you're right. Not really, not much. Maybe it's not measurable. I take this rubber ball and I build a machine because I'm a wacko, and I bounce the ball 1,000,000 times a second on the floor, and the ball's made of lead. All right? The floor get hot? Yeah, the floor is going to be red hot. Yeah, of course it's going to be. All right, now I get a red hot floor, put a ball on it. Does it shoot up 1,000,000 times? No, not might do it once. It's not going to do it 1,000,000 times. All right, that's another way to put it. And why is that? Okay, here's another example. All right, so I compress a gas, and all those gas molecules, I remember on day one, I said, no, sorry, day three, I said I whacked a gas molecule. I whacked a gas molecule, and that's work. And that's work because I'm on the outside, and I see it in action. And those gas molecules, they got hit like tennis balls. They all started going that way. The problem is they don't come right back at you. You know, come at me, bro. When you hit them, they go this way, but they don't exactly bounce back against the wall and come right back at you. That means if I compress the gas, it would knock me back. Well, it doesn't. I mean, it's not like it's easy to compress the cylinder because we're above that atmospheric pressure, and I have to put some force in, but it's not like as soon as I do it, all of a sudden those bastards come right back at me, and I'm like, whoa, damn. You're in the wrong fret. So it's because those gas molecules, as soon as I hit them, and they do have that coherent motion, that work, they lose it. They lose it and they start whizzing around other directions. If they just wouldn't do that, I would get knocked backward on my ass. I could build a perfect engine, and I can't. Everything would be 100% efficient, and it's not because of the second law. All right, so it's the source of the second law is that nature is random, and when you de-randomize it by doing this, by hitting those molecules in one direction, which is not random, they will become random really freaking fast. I looked this up. So what and how fast? Okay, so I hit those molecules in the magic cylinder. How fast did they randomize? Seconds? About 10 to the minus 9 seconds. 10 to the minus 9. Now, you perceive light at around a 10 millisecond rate. Your eyes, your ears. That's electrical impulses to your brain. Your brain makes a decision. It says, yes, I'll have another. And so it takes 10 milliseconds. I'm faster. But so 10 milliseconds is 10 to the minus 3 times 10 to the minus 2. So 10 to the 7 is 10 million. So 10 million times faster than you can perceive light itself, those gas molecules have rearranged themselves and are now behaving randomly, whereas they weren't before when you did the work. A liquid? Guess what? Slower? No, faster. That's about the limit that people can make measurements. We have really fancy, crazy laser stuff. This is what I used to do when I was a real physical chemist. And this is as fast as a measurement can be made with insanely expensive lasers. I still do this stuff every now and then. And in a solid, even faster. This is 10 to the minus 13. Okay, that's blindingly fast. That's so much faster than you can operate that's why the second law exists. And that's why you do some work, you do some heat, but the heat's moving randomly. And it's going to move randomly, no matter how you create the heat. Even you create the heat with work, it won't go backward. Because once they first started moving in a certain direction, they started moving in all directions. And so they just don't come back at you. So you just can't turn that heat to work like you can turn work to heat. And that's, again, because one way is directional, one way is sensible, but the other way is random and chaotic, and that's the one we actually care about, because we power the planet with heat and not work. Last one, pinball. Okay, again, just explaining this over and over and over again, just so how you think. Pinball. You don't have, you came to me, yeah, I was in the arcade and I got 0 at pinball. I'm like, well, you didn't play the game. Because no, I mean, no matter how stupid you are, even if you have no arms or legs, you can still grab the plunger with your mouth and pull back. And if you play pinball, you've got points. So now you come to me and say, well, yeah, I got 10,000 points on pinball. I'm like, okay, yeah, all right, you played the game, all right? So you did some heat. But how did you do it? I don't know. Because pinball is random and chaotic. So while I know you played the game, I would never figure out how you played it. You know, how the ball moved randomly around, or how far back, a little bit, excuse me, how far back you pulled that plunger. If you actually played pinball, just, oh my God. You know 10 years ago, everyone would have said, oh, you raise your hand, you just got an extra 10 points on the test. Just kidding. I'm that old. Internet wasn't invented until I was 21 years old, actually. Okay, so anyway, all right, I'm just talking. Start drawing. Again, I just want you to hear it multiple ways. I think that's better for you. And now let me draw it out. This is, I know you engineers have seen this, you're probably sick of it. You sleep like the guy at the top. Okay, so this is how this is drawn. Hot, cold. So this is heat. Of course, there's only changes in heat. This is work. Okay, now what the second law says is that you can't do this. Again, just another way that this is very commonly expressed. And so, you know, despite my wonkiness, I do want to make certain that you hear things the same that you hear it anywhere else, no matter who's teaching it. That's pretty important. I want you all to be competitive. The second law says you can't do this. Second law says you're going to do this. All right, so it means two things. For one, all engines, as I go over engine design, and if you looked at your homework set, you may have noticed that there's a lot of questions about engines. Actually, some of the compression problems I had you do are actual numbers from working engines. And I also obviously do the power plant thing, because, I mean, that's important, that's relevant. A lot of you are engineers, so you need to know this stuff. This would be worked out, so this would be negative work. That's a detail, don't worry about it. What it says is two things. Again, I've got a hot block and a cold block. Now, as you're going to see, all engines have to have that. They have to have somewhere inside of them a differential. Maybe engineers are thinking nuts and bolts, but I don't care about that much. I'm thinking more big picture. That's kind of more my job as a chemist. That's why we're smarter. Edit. Now we do tend to think not so much about nuts and bolts, but if you think about your nuts and bolts, somewhere in your engine you have something that's hot, and somewhere else you have a part that's cold. It has to be that way, or the engine doesn't work. So you've got a hot and a cold block. The other thing is that you're going to lose some heat. No matter what, you add heat to the balloon. Yes, it'll expand, but it still gets hot, and of course then it cools. That's what that says. Now you know that. Again, intuition does kick in. That's a very good thing, especially about this one. So, engines. Yeah, I've got plenty of time. Let's see. Do I want to tell you about this? Not yet. Not yet. Okay. Now, I got a really cool example coming up, but I'm not going to tell it to you yet. Okay. So, Carnot. Sadie Carnot. Sadie Carnot was the first thermodynamicist. He was French, which is terrible. Oh, come on, you gotta have some nationalism. So, Sadie Carnot was a French guy in the 1850s. He was actually a cannoneer. They actually had those back in the day, cannoneer for Napoleon. So he shot cannons all day. And one day he starts thinking, he's a young guy, and he starts thinking, why does this work? Why does the ball shoot out of the thing? Well, I mean, because he blew something up. But no, he was, well, yeah, all right, that's true. I'm sure he knew that. But he wanted to think more about, really, why does this ball go so far when I add this much gunpowder? He was just thinking about this stuff. And he was the first guy who, he didn't predict entropy. Now remember, again, we're living in a time that people don't even know that air is there. They think it's something else. They don't even know molecules are there. And more importantly, doctors would deliver baby after baby without washing their hands. That's why most of them died. And, you touch the body of the dead, which we do not do anymore. So he lived in a very backward time. But he figured out a lot about thermodynamics, he understood why they came in shock, he wrote a lot of things down that were completely correct. People ignored it, and actually people like Henry Ford started building gas engines without understanding thermo. Just sorry for you engineers, right? Well, no, this is good about engineers. Engineers started designing engines efficiently without knowing the laws of thermodynamics. So people had built their first reciprocating engines, and they were like, and they designed it, they kept tinkering and designed it worked really well. And then one of them read Carnot's papers, and they're like, oh, well damn, this is actually why this works. So the chemists did not actually tell the engineers what to do. The engineers proved the chemists were correct without even knowing it. That you don't care, do you? Anyway, all right. So Carnot figured out a lot of thermo, and he knew that there was something there. He wasn't sure what it was, but he was doing calculations with entropy. It's just entropy was this question mark. He just didn't know what it was. Now he died at age 34 from cholera, and right before he died, he started telling people that he had figured out something big, something really big. And there were notes in his house about what was trying to come out, right? And again, people didn't listen for a long time, but no one knows what that big thing was because he kills over dead of cholera, 1850. People started to figure out that you needed to wash your hands. People started to figure out that when you drink the muddy water, you keel over dead. People started to figure out when you fall over from cholera, you don't touch them, you burn the body where it lies. You don't go into their house, you burn it to the ground, which they did with all of his notes. So, no one knows what he figured out. Maybe he figured out quantum mechanics. And he did. God, they would have had such incredible things like lasers and nuclear weapons. I mean, a Napoleon could have had a nuclear weapon. God, I want that to happen just to see what would have happened. You know? So no one knows what he came up with. But anyway, I do like you guys to, know about these people. They are pretty interesting, and they did neat things with their lives, and so will you. And so you want your own story told at one point. Carnot figured out one thing, that a really useful engine has to do this. It has to reciprocate. I'll draw that best I can. I'm just not having a good handwriting day. So he figured out that, all right, so when you were a little kid, you probably had little toy cars that operated on springs. Just fine. You wind up the spring, the little car goes, and hell, you're only 5 years old, so really anything to entertain you. But that's not a good way to make an actual car work. So a spring is an engine, is a source of power, but it just expels and then it doesn't come back until and then you have to wind it up again, whatever, don't worry about it. It does its work and it's done. Carnot knew that that was not good. He knew that you had to have a motor turn a shaft in a circle. That's not a spring. The spring may be moving in a circle, but it only moves one way. This moves two ways. It goes up and down. Springs don't. Springs only go up. Right? Think of it that way. So Carnot knew this was the heart of the engine. Now remember, I told you, and it makes a lot of sense. I talked to you about how energy has to work in an engine. It has to be a power stroke. The power stroke is an expansion. The power stroke is negative work. Because look at it. Look at it. Think about this now. I'm holding on to the camshaft, and underneath me is a piston. It's the upswing. It's the expansion that is the power stroke. Now, the downstroke, the compression stroke, is a little harder. That's where the engine actually works. But you can just see it. Just look at it. It's obvious. Up drives the engine. And that turns the wheel, and down you go. Then you have to return. The return is everything. This is what Carnot figured out. The expansion is hard. The compression that makes the engine work the way it does. I know I'm running my mouth because I didn't deliver much of a lecture. But let's do this. All right, so I'm going to do an isotherm. So what we're going to do is, there's a region, off my game today. There's a reason that cars have engine blocks. It's a source of heat. It's a heat block. And so what we're going to do is expand that piston at constant T. Okay, so we're doing the power stroke, and this is an isotherm. And the work is minus nRT. We're going to do it reversibly because that's, we already know this kind of stuff Carnot figured out. We already know that reversible work is the most negative. And again, the power stroke is a negative work. And ln Vf over di. Okay, now, Again, Carnot knows, he knows that we have to build reciprocating engines. So that's this way, and then he figured out, well, let's go back. Okay? So that's going to be plus. Now we're going to add work like before, like I screwed up on the implement question. Okay? So, work energy adds. If it chooses to be negative, it will be negative, but whatever. Now, sorry about this. I know this is a wacky way to do this. One of those identities that you know in the back of your head. If you need identities, what did I? Sorry. No. I didn't. Right, I had to switch them. Sorry. All right. So there's no NRT, VF, VI. But of course, if we're going to reciprocate, I just permute those. Sorry, I didn't point that out. So that's obvious. But I want to point out that that is equal to plus natural log of A over B is minus natural log of B over A. Again, an identity that you should have in the back of your head, and if you don't, that's fine. If you need it, it's on the cheat sheet, which is sent to you on Wednesday. Okay, so you can see that, sorry, changing word. Sorry, God. I don't know what's wrong with me. Okay, change of work is
0.
Thank you, someone, I know who you are, anyway. Yeah, 0. You didn't do any work. Now, what that means is the power stroke fired and the car lurched, but the compression stroke happened and you went right back. That's actually what that means. That's how the engine's working. That would literally happen if this was how your engine was designed. It really wouldn't go anywhere, just shuttle and just shake and shimmy, but it wouldn't do anything. Okay, now remember that work, let me put this to vote. Remember that work is the area under the curve, and direction matters. That was your second problem set. So the area under the curve matters, direction matters. This one was a negative work, because there's area, and I pick up a minus sign because of impact. Then I went backward, picking up a second negative sign. The area under the curve is now positive, and they cancel. I need them not to cancel. Now, there's not a lot I can do about the expansion stroke. I mean, I have to have that. But the compression stroke, the compression stroke, what can I do? Any suggestions? What, this curve to the left, what can I do? I mean, you engineers, you already know, don't you? You just don't want to say so, give the chemist a chance, which I actually appreciate. Well, think what can I do to lessen the area under the curve of the left-hand stroke, the compression stroke? Lower it. Right. Drop it. Let it go back, and then raise it back up again. There you go. Now I've got net negative work. Net negative work is, again, the sensible way to make the car go down the street. Now, next question. How do I lower it? Huh? Seriously, all right, now, okay, think about this. I'm not going to change volume, but I'm going to lower pressure. What can I do?
Temperature?
Lower the temperature. Right, exactly. Lower the temperature. That drives it down. So you have to have this fantastical structure that will expand a hot gas and then expel it at a lower temperature. Okay, expanding a hot gas. Where's the hot gas come in your car? It's literally the gas, right? And it does what inside the piston? Right, it burns. That's the spark plug. Actually, diesel engines don't need spark plugs. The compression actually generates enough heat to burn them. That's why diesel engines are kind of cool. Okay, then another valve opens up. So then actually the fuel air mixture is compressed. The spark plug fires. You get your power stroke. So this is why Ford Auto Diesel, actually, the guy's name, no, it wasn't Otto, it was Roland or something like that. Anyway, the guy named Diesel figured this out. He figured out 4-stroke engines. One is compress the fuel air mixture, the spark plug fires. Then you get the important stroke, the power stroke. Then a valve opens up. To let the gas out, and the return stroke pushes the air out, and then the 4th stroke sucks more gas in. So that's how an engine works. I'll put a little GIF up on the website. Okay, so what's important about that? Again, the engine has a heat block. Engine block is a heat block. So that's this part here. But an engine is connected to a tailpipe. Your tailpipe, all right, on these muscle cars, where are the tailpipes? I know the tailpipe for most of your cars is underneath your car. It's on the sides. Are they big? You know why? Keeps them cool. That's your cold block. Your hot block, as I drew up, as I drew here, here's your engine block, the hot block. Here's your tailpipe, that's the cold block. That's your heat differential. That's why your engine works as well as it does. Not that well. So this is the gas firing, that's why it's hot. The gas gets exposed to the tailpipe, which is cold. And that's why the engine works. Okay, so last bit. I'll introduce this and I'll go over it more on Monday. I'm really running my mouth. I'm getting myself confused today. I don't know why. But this is something called a Carnot cycle. And it's kind of painful what we're going to do on Monday. So just work with me on that. P versus V. What we're going to do is design the, we're not going to worry about the fuel stroke or first you compress the fuel air mixture, forget about that. You do the power stroke, you do the exhaust stroke, and then you do the part where you suck the fuel in. We're going to forget the first two strokes, we're going to do the middle two, which are the important ones. And what we'll do is we're going to expand something. We just burned gas, it's hot, it expanded. All right, but then we're going to cool it. Now, you know what would be great is to cool something and still expand. That would be nice. How can I do that? How many of you looked at your homework question? Adiabatic expansions, hello? Sound familiar? Right, do the adiabatic expansion. Isothermal, adiabatic. Remember, an adiabatic expansion will accomplish two goals. It will cool the gas down and give you some more expansion, which is more power stroke, a little bit extra. So you win-win. Then you're going to return. Okay, this is the gas expulsion. You're going to do that isothermally. That's because the tailpipe is at a certain temperature. And then you want to cool, and yet you still got to expand. Sorry, you got to contract still. Sorry, God, I'm so out of it. I almost don't. This cools so that you can, you can contract at a lower temperature, but you got to heat back up. So what you're going to do is contract under adiabatic conditions and get your temperature to rise again. And this is a Carnot cycle. If you look at Wikipedia, there's actually several different cycles, including a diesel cycle, but Carnot's is the best. It turns out that if you design an engine to do exactly this, isothermal expansion, adiabatic expansion, isothermal contraction, adiabatic contraction, if you build the engine that works by these principles as best as you can, that is the most efficient engine that you could ever build. The other cycles, like the diesel cycle, actually, that's actually a diesel cycle right up there. And it's not as efficient as a Carnot cycle. And then there's 2 or 3 other types of cycles. So what we're going to do next time, I'll end now because I'm just walking around with a fish. We're going to add up the work and then add up the heat. And because we divide the car by burning, we're going to divide the two, and that's going to be our engine efficiency. And anyway, so I'm going to go look these things up. I'm sorry I was just flipping fish. I'll get out for some Hershey's if you feel like it. So I'll see you on Monday. Email me with questions. I'll see you on Tuesday and Wednesday.